All right, 3.5 continued. First of all, I thought that it might be a good idea to remind you of a few trig identities. Tangent of x, sine over cosine. Cotangent is the same as 1 over tan, which is also cosine over sine. It's very equivalent. Cosecant of x is equal to 1 over sine of x. Secant is 1 over cosine, and sine squared plus cosine squared is equal to 1. There are variations on this one. They don't come up a lot, but they're certainly not non-existent, so they will come up some. But these are the big ones, all right? These are the ones that you should probably memorize before you take the AP test. Okay, so there's that. Remember that we are building on these, using these derivative rules for trig functions, and I think we can get right into it. So so we used the derivative of sine cosine in the last video quite frequently. Or at least in a few examples. Let's do another derivative, but let's not use the sine and cosines. Let's take, in fact, let's bundle a couple things in one here. Let's find the second derivative of this, secant of x plus sine of x. And what we want to do is find f double prime of x. So we want to find the second derivative here. Okay. First derivative. Well, this is a sum of two functions, so what we'll do is we'll take the derivative of the first plus the derivative of the second. Derivative of secant. Check my rules. Looks like it's secant times tangent of x, so I'll write secant times tangent. Derivative of sine. It's cosine. Okay? First derivative done. Second derivative. To derive secant times tangent, we're going to have to use the product rule. So that'll be the first derivative of the second plus the second derivative of the first, and then we'll deal with cosine on its own. So let's do that. So the first function is secant times the derivative of the second. Derivative of tangent is secant squared. By the way, you should, of course, pause and try this on your own. See how you do. Plus the second, which is tangent of x, times the derivative of the first, which is secant tangent. Plus the derivative of cosine, which is negative sine. Excuse me. Okay, barely got that in on the sheet of paper there. All right, we got to clean this up. There's no way that we could live with ourselves if we left this in this format, our answer in this format. So we have secant times secant squared. That's going to be secant cubed. We have tangent times secant times tangent. Associative property says that I can go tangent times tangent, which would be tangent squared, times secant. In fact, let's put the secant first. Not that it matters. Secant x times tangent squared x. Plus the negative, it's minus. All right. And I don't think that it gets any simpler than that. I think that's pretty much where our final answer is going to rest. All right, so there's the second derivative of that one. And I don't think I need to do a ton of examples. A lot of this is just going to be using those derivative rules in certain contexts and being very careful with the simplification. And if you can identify any identities that are useful, so like sometimes this one's going to come up, sometimes it's helpful to turn to cosines and sines, then you're more than welcome to use those, and you should use those, but there I don't think that's going to get any simpler. All right, let's talk about jerk. Okay, so what is jerk? Well, to define jerk, we need to start with the position function. Okay, so let's do this. Let's define s of t as position at time t. Okay, so start with the position function. If I do that, then s prime of t, the derivative of s with respect to t, so I guess, do I need to write that out? I guess I will once. Okay, s prime of t is the derivative with respect to t of s of t. And the derivative with s turns out to be velocity. Okay, in other words, the change in position is velocity. Okay, so then if I go from there, if I take the second derivative of s, so s double prime of t. That would be equal to v prime at t. In other words, that would be the derivative of v of t. That turns out to be acceleration. The change in velocity is acceleration, the definition of acceleration. Okay, so you can feel this so I'm going to go back to the car example a couple times here, but you can feel that in a car, right? When you're accelerating, your velocity is changing. Most students can imagine that and don't have any trouble wrapping their head around that. What about the third derivative? In other words, the second derivative of velocity. In other words, the derivative of acceleration. In other words, the change in acceleration. Think about what that might be. So this is s triple prime of t. And that would be v double prime of t. That would be a prime of t. That would be what we call jerk. Okay, j of t, right? And this is jerk. All right. So think about for a second, what is the change in acceleration? Well, you can, if you're in a car, right, and you're accelerating at a constant speed or a constant rate, I guess you might say. Your rate of acceleration is constant. It doesn't. You're not going to feel a lot. Like you might feel pressed up against your seat, right, because you're accelerating. When there's a change in acceleration, so let's say that you're accelerating and all of a sudden you slam on the brakes, then you're going to get a sensation of, you will feel that, and that change in sensation from the change in acceleration is called jerk. Jerk is what makes you sick on roller coasters. It's the change in acceleration. If you are going down the hill and you're accelerating at a constant speed, going down the roller coaster, that's not likely to make you sick. But when you hit the bottom and then you come back up, that change in acceleration, that abrupt change in acceleration is what is going to kind of jostle you. Okay, so that is what jerk is. It is just the third derivative of position. So, if you are given, I guess we'll do just one example here. So if you're given that the velocity, position function is equal to like 7 cosine of t. Like it might be if you had like a weight bouncing on a spring. Okay, where it bounces up and down, and you wanted a graph of the position, might be something like this, 7 cosine of t. And we say, well, what is the jerk? Well, you would just take the derivative of s, so the derivative of that would be v. So v of t would be equal to the derivative of 7 cosine, which turns out to be negative 7 sine of t. And then you take the derivative of that to get a, so a of t would be equal to, so derivative of sine would be just cosine, so you'd have negative 7 cosine of t. And then to get the jerk, change in acceleration, you would just take the derivative of a, which is, so derive cosine, you get negative sine, negative is a positive, so I think you end up with 7 sine of t. And is that what I wrote down? Yes, it is. Okay, so that's how you'd find jerk. Just the third derivative of position, but a good thing to know. And students sometimes ask, what does the derivative of jerk mean? I have no idea. It's the change in jerk. So for our purposes, we don't need to go beyond the third derivative of position. So, and that, I think, finally wraps up section 3.5.